Hello, welcome everyone to our presentation of findings about the Regent Sea Glider. So we'll introduce the glider first and explore the benefits. The glider is an all-electric aircraft that combines capabilities of a boat and a plane. As I mentioned, it's all electric, so it produces zero emissions and it's eliminating a large contributor of fossil fuel emissions from air and water travel. Reduced travel times are now possible due to the speed of the glider, as well as lower fuel costs, which means um, lower cost to travel. So everybody benefits. Finally, you guys that are watching will learn about the science behind some sustainable technologies, which you can take with you going forward. So to start this presentation, Jayden will talk about electric propulsion, which is the concept behind the electric propellers of the glider. Next, Thomas will talk about the battery and the endurance it provides to the glider. Next, I will talk about the navigation and the control system of the glider, which allows it to fly safely close to the water. And then finally, Mitchell will talk about the hydrofoil and hull design, which describes how the glider moves through the water and the air.
So, hi guys, my name is Jayden, and I want to talk to you guys about electric propulsion. Electric propulsion in today's times are seen in space applications, such as to get satellites up to orbit or to launch spacecrafts. But what we're trying to do is to get it into more common and general purposes like boats, planes, and gliders to try and help the environment a little bit. So, electric propulsion occurs mainly due to a principle called Faraday's law. Faraday's law basically says that an electrical current or voltage can be turned into a mechanical force using magnets. It can be shown here as the magnet moves inside of this coil, the current is going to increase on the meter. So in terms of the glider, this theory is used in electric induction motors. An electric induction motor looks like this, and it consists of two parts. First, we have the stator, which is a stationary piece that consists of a bunch of copper coils, which are seen here, which are given a voltage and magnetized. The rotor consists of an interior shaft that's lined with a bunch of magnets, which are at slight angles. So when the motor is given a voltage, like so, the copper coils will start to generate a magnetic field inside of it, which will make the magnets on the rotor start to spin. This spin is known as mechanical force, which is technically a torque. So the way that this turns it into forward motion is through the use of propellers, which are attached to the shaft. And what the propellers basically do is spin at high speeds to cut through the air and move the craft forwards. By use of a flight controller or other systems, they can be tilted up and down to control the altitude of a plane, or in other words, the lift. Next, I'm going to be introducing Thomas, who's going to talk to you about the battery.
Hi, I'm Thomas, and someone might ask, how are those electric planes powered? Are they like those remote-controlled planes? Surprisingly, it's actually very similar, but also on a much larger scale. Unfortunately, we can't stuff any of these batteries seen here into the plane to make it work. They are much bigger. Key differences in how an electric plane works and a normal airplane works is that fuel is needed to power the turbo engines, while an electric engine uses something else. Can you take a guess? That's right, it's electricity from a battery. The redox reaction is the basis of how any battery works. If you paid attention in chemistry class, particles can share electrons, which charge each other. In a redox reaction, a particle is oxidized, which means it gives electrons away, and a particle is reduced, which means it receives the electron. It's called reduced because the charge level is lowered by gaining this electron. In this picture, particle A shares its electrons with particle B. It's very simple. Now, a battery. How does it really work? There are four main components of a battery, as seen here. The really important ones are the anode and the cathode. Remember particle A and particle B sharing electrons? Imagine that, but on a much larger scale within a battery. See, sad frog. Sad because it has no power. The act of sharing is truly wonderful, even to things that aren't even alive. By sharing, the flow of electrons from the anode to the cathode provide power to the now happy frog. Batteries come in all shapes and sizes. However, airplane batteries come in more specific shapes and sizes. Battery cells are put into packs like this. And these packs are put into casings so they can be easily removed or added to an electric plane. Now, how long can the Regency glider last? At full charge, when going at top speeds of up to 180 miles per hour, it can travel over 180 miles, which means it will last up to 1 hour per full charge of battery.
Okay, so now I'm going to talk about the control system. Many people, potentially some of you guys watching, have a fear of flying, which is, when you think about it, actually quite irrational, since you're more likely to be struck by lightning than to get in a plane crash. And although the chances of getting a plane crash are so low, it's still a common phobia. Therefore, if the glider is ever to become a standard form of travel, people will need to have trust in it. And this trust takes a long time to build, and one crash could be enough to just discontinue the entire project. So with this in mind, the importance of the glider's control system cannot be stressed enough. So we're going to be looking at how the glider flies safely at low altitude, which would be a large concern for passengers of the glider. In order for the glider to maintain its altitude and for it to fly in a steady path instead of veering up and down, we need a robust control system. And one way to do this is to apply a PID controller, which stands for proportional integral derivative. If these terms are unfamiliar to you, do not worry. We just need to know what they do. So the PID controller accounts for present error, which is done by the proportional term. It accounts for past error, which is controlled by the integral term. And then finally, it anticipates future error, which is controlled by the derivative term. So the goal of combining all of these controls is to have our altitude here, have our altitude here, and have our altitude here all remain the same. So while flying, the glider constantly measures its altitude. It measures it periodically, and thus we can plot it as a function of time. Now, our desired altitude, where we want the glider to stay, is inputted manually. And for the sakes of this demonstration, we'll say it's 5 meters, and it's going to remain the same for the duration of this flight. And this is referred to as your set point. In other words, your desired altitude. Now our actual altitude, we'll say, starts at around 0, and then it increases, and then it overshoots potentially, comes back, and then finally it settles after a while. Now this is an example of a bad response. This is not safe. No one is going to want to fly in this glider if it's veering this much up and down. And so the main properties that the control system is trying to fix are what's known as the rise time, which is how long it takes the altitude to initially reach its desired value. The overshoot, which is how much it overcorrects by, which is here. And then finally, this final difference once it settles, which is known as your steady state error. So it wants to essentially improve these three features. And so the proportional term improves our rise time. Our derivative term reduces our overshoot, and our integral term reduces our steady state error. So the integral term works by calculating the area between our actual altitude and our desired altitude. Calculates this area here, and then applies a correction based on that. The proportional term simply calculates the error at a specific time. So at 3 seconds, our error would be 2. And calculates that and outputs a simple correction based on that. And finally, our derivative term calculates the rate of change of our error. So if we were to calculate our rate of change here, we see that our altitude is increasing very quickly. But if we were actually to take the error, it would be decreasing, because our error would be our set point minus our desired altitude. And so this decreasing error means a negative rate of change. So it's going to subtract from the output of the glider, preventing this overcorrection. Combining all of these together should produce a nice steady response where we arrive at the altitude quickly and remain there. And when applying this to the glider, we want to focus on the integral control, which eliminates this steady state error, because we're focused on keeping the glider steady while it's in flight. Second would be the second most important term would be the derivative term, because we don't want to overcorrect, because if we overcorrect here, there's a good chance we'll overcorrect here, and that will be too close to the water. And finally, our proportional term is the least important, because we don't care as much about arriving at a desired altitude as we do about staying there. And so combining all of these together means that we have happy and safe passengers, and our fear of flying no longer exists, hopefully. So with that, I'll pass it to Mitchell.
All right, thanks, Matthew. My name is Mitchell, and I investigated the hull design of the glider, particularly the hydrofoil. Before we go into the design, we're going to talk about drag. Now, has everyone biked into a headwind on a windy day? The answer is probably yes, and you've probably noticed that it's much harder than biking into a tailwind. Now, the reason for this is drag. Drag is defined as the force opposing an object's motion through space. Why is that something you care about? Because it's something that affects everyone and everything moving through space. Minimalizing drag allows vehicles to be more efficient, allows them to travel longer and travel faster. The Sea Glider is designed to minimize the 4 factors affecting drag, which are cross-sectional area, density of fluid, speed, and the shape of the glider. These are best understood by comparing the difficulty of running in various circumstances, as seen on the next slide. So objects with a larger cross-sectional area, like a parachute, make moving through space much harder. So it makes it harder to run. The next is density. If I asked you to run through water or run through air, which would you pick? Probably air. And that's because water is more than 830 times denser than air, meaning it requires a lot more work to move through. The next is speed. If I asked you to run 2 kilometers as fast as you could or walk, what would you pick? Unless you're a track star, you're probably picking walking. That's because the faster you travel, the more resistance you must overcome and the more work is required. Now you're probably wondering, is this the reason Usain Bolt is so fast? No, not quite, but that's a different thing altogether. Finally is the shape. If I asked you to run 2 kilometers holding a large blunt object like a parachute, would you do it? Probably not. That's because aerodynamically blunt objects like the cube or a parachute are not efficient and make it a lot harder to run. Now, all the properties acting on a person running act the same way on the glider. The most influential being density of the fluid the glider has to travel through. As you can see in the next slide, the hull is very streamlined and has a small frontal cross-sectional area here. These are the 2 hydrofoils coming down for the front, which are the key elements of the glider success. This image kind of helps demonstrate how the gliders work, or sorry, on the next slide. As you can see, it's hard to show, but this top line is slightly longer than the bottom line. And that creates because the air has to travel across this foil is fixed, it means the top line has to travel faster because it has to travel farther. And so this causes a pressure difference between the top and the bottom. And this is what produces this lifting force. So the high velocity air on top creates a low pressure region and an inflow of mass. And so if I show you blow on this piece of paper, it has the same effect. So the high pressure or low pressure area up here causes the mass inflow and an overall lift. Kind of cool, right? Now this principle is exactly how the glider's hydrofoils manipulate the water to produce a lifting force. As the glider speeds up, the hydrofoils generate more and more lift, and the more lift produced, the more the glider rises out of the water. The more the glider rises out of the water, the easier it is because it has to only go through air instead of the high density water, like running through air instead of water. So in conclusion, the glider's minimal cross-sectional area, streamlined body, and hydrofoils all play key roles in allowing the glider to travel like both a boat and a plane and make the glider a revolution in coastal travel. So those are our topics. We hope you found the presentation on the electric propulsion, the electric battery, the navigation system, and the hull design of the Regent Sea Glider informative and interesting. The glider has the potential to completely change coastal travel and is going to be a large step forward in the fight against climate change. Thank you for listening. Take care.